Hi everyone, welcome to my channel. Today I am going to do the seminar on research concerning the equation of state of gases and liquids. Let us do research now. We know that what is meant by gases and what are liquids. The intermolecular force of attraction is more in liquids than in gases. That much is enough for us now. Now, this is the research concerning the equation of state of gases and liquids, that is by Vander. Let us see what are the topics we are going to discuss. That is introduction part, theory and experimental analysis, merits and demerits, and lastly the conclusion part. First is introduction part. In 1873, Johannes Vander formulated an equation of state that applies to both gases and liquids. Means he formulated an equation that is based on that is the modification of an ideal gas. He formulated that equation in 1873, and later he says that it doesn't obey the laws. Means it doesn't obey the law strictly. This equation doesn't obey the laws strictly under high pressure. Next, he gets the Nobel Prize in 1910 for his work on equation of state of gases and liquids. That is the Johannes Vander equation. The equation which was modified by the ideal gas equation is the Johannes Vander equation. Why he modified? What are the experimental studies? What he made? Let us do in the slides. That is, first is what is meant by Vander equation. It is an equation which relates the pressure, volume, temperature, and the number of moles. And next is what is ideal gas equation. According to Boyle's law, at constant temperature, volume is inversely proportional to pressure. And similarly, Charles' law, at constant pressure, volume is directly proportional to temperature. And Avogadro's law, at constant pressure and at constant temperature and pressure, volume is directly proportional to number of moles. And by combining these three equations, we will finally get the ideal gas equation, that is PV is equals to nRT, where the proportionality constant is said to be the universal gas constant or the ideal gas constant, that is the R. Here P is the pressure of the gas in the container, whereas V is the volume of the gas in the container, or we can say in space also. In similar way, the temperature. And next, an ideal gas is defined as one in which the collisions between atoms or molecules are perfectly elastic. Means it regains its original position. So there is no change in volume of the gas in the container, or we can say in space. And there is no intermolecular force of attractions between the molecules. According to kinetic theory postulates, these two are said to be the postulates of kinetic theory, and these are hold good for the ideal gas equation. So therefore an ideal gas equation obeys the postulates of kinetic theory of gases. And next, what defines the real gas? Means until now we have discussed what is an ideal gas. Means ideal gas is a gas which strictly obeys all the laws. So that is called as an ideal gas. Then what is real gas? A real gas is the one that deviates from the ideal behavior due to the effects of the gas particles occupying a finite volume and the strength of intermolecular forces. Real gas obeys gas laws only at conditions of low pressure and high temperature. Means real gas obeys the gas laws only at low pressure and high temperature, but in high pressure it doesn't obey. Let us discuss later why it is so. First, the experimental analysis made by the Vander. Here you can see the two graphs, where the first graph is drawn between the PV versus P. Here we know that at constant temperature PV is equals to constant, right? If PV is equals to constant, then we should get the straight line parallel to x-axis. But we are not getting so, because all the gases are showing both negative deviation and positive deviation. It is why so. And next, in similar way, they have drawn the graph between pressure and volume. Here the real gas is covering more volume than the ideal gas. So why it is so? At high pressure, real gas is covering more volume than the ideal gas, and here the at low pressure both coinciding. We can see they both show the ideal behavior at low pressure, but at high pressure real gas has the difference. So why there is a deviation? Now we are with the two questions. Why do gas deviate from the ideal behavior, and what are the conditions under which the gases deviate from ideality? And next is pressure correction and volume correction. Pressure correction. We know that according to kinetic theory, there is no intermolecular force of attraction, and there is no more intermolecular force of attraction, and the volume of the molecules are negligible in size. But in Van der Waals equation, or we can say in real gas, it doesn't hold good. If it hold good, why in last graph we have seen why there is a deviation, means why there is a volume difference. They should coincide with each other if there is no difference. So there is a pressure correction and volume correction of ideal gas equation. How it does? Let us see. Then this is the experimental pressure, that is observed pressure, or we can say ideal gas pressure, and this is the corrected pressure, means due to the intermolecular force of attraction there is an influence on pressure. How it is influence on pressure? We know that pressure is equals to force per unit area. So if there is an effect in force, then it must affect the pressure. So there is a pressure correction, and we know that there are two types of molecules here. Here you can observe there is a two types of molecules. So the pressure correction, that is there is an addition of pressure, and due to the intermolecular force of attraction. This correction is due to the intermolecular force of attraction. At low pressure there is no pressure correction needed, but at high pressure Van der Waals assumed that there should be a pressure correction needed. So according to intermolecular force of attraction, if the pressure is high, then the intermolecular force of attraction plays an important role. So how it plays an important role? If the pressure is directly proportional to the one type of molecule, that is number of moles per unit volume, or we can say number of moles per volume for one type of molecule. In similar way, for another type of volume also it is directly proportional to the number of moles per volume, and by combining these two we will get n square by v square, and the proportionality constant is taken as A. This is the pressure correction. And next the volume correction. As there is an intermolecular force of attraction, both molecules will combine to form only one molecule, like both the radius are there is an excluded volume. Both molecules combine to form one molecule, so there is an excluding volume. So there is an volume correction. Finally there is an volume correction, and as we know that according to Galois's law, pressure is directly proportional to temperature. So it depends upon the particular gas, where if pressure is high, then temperature will be high according to Galois's law. And at high pressure these laws are not strictly obeyed. So there is a correction of ideal gas equation, and finally we are with Van der Waals equation, that is P plus AN square by V square into V minus NB is equals to nRT, where A and B the Van der Waals constants, and the unit of A is given by atom liter square per mole square, and unit of B is liter per mole, and R is equals to 8.3144 joule per mole per Kelvin, that is the unit of universal gas constant. And next is compressibility factor. What is meant by compressibility factor? It is a measure of deviation of the real gas from the ideal behavior. Z is equals to PVN by RT. That is the equation for compressibility factor, and this is the mechanism on which Van der Waals equation run. Okay na? For ideal gas equation, PVN is equals to RT when Z is equals to 1. When this ratio is equals to 1, then we can say that it is equal to 1, it behaves like an ideal gas equation. Or else what else it behave? Means we can say in other words, this compressibility factor can also be defined as it is a ratio of volume of real gas to volume of ideal gas. Okay, now that is another definition we can say. And if Z is equals to 1, it behaves as an ideal gas, and if Z is greater than 1 and PVN is greater than RT, then the gases have compressibility greater than 1, have a positive deviation, means it have a positive deviation from the ideal gases at all the temperature and pressure. Hydrogen, if it has the positive deviation, you can observe that there is a force of repulsion between the two atoms. And hydrogen and noble gases except krypton are the examples of this positive deviation. That is, the force of attraction is less in Z is greater, if Z is greater than 1. Okay, now next comes the Z is less than 1. If it is Z is less than, means compressibility factor is less than 1, then there is a force of repulsion. So okay, now there is a force of repulsion in negative deviation. The gases have compressibility lesser than 1, show negative deviation from the ideal gases at all temperature and pressure. So hydrogen and helium are the examples for this. So the compressibility factor is over, means these are the experimental observation by the Vander Waal. So he made the correction, and he also found out that there is a compressibility factor where it determines how the ideal gas behavior. Ideal gas shows the deviation from the to real gas, how it shows. And here are some gases which are deviating from the ideal to real gas, you can see here. And next, outcomes. Has every experiment has positive outcomes and negative outcomes. These arrow marks indicates the positive outcomes, and these dot marks indicates the negative outcomes. And positive outcomes are able to predict the behavior of gases better than the ideal gases equation, means Vander Waal equation will explain the behavior of gases better than the ideal gas equation. And it is also applicable to all the gases, but for also fluids also it is applicable. And it is also able to calculate the critical conditions of liquefaction. That is, we can further calculation, means further after doing some calculations in Vander Waal equation, we will get some volume ratio and temperature ratio, and that conditions are used for the liquefaction. And in similar way, there are negative outcomes. That is, the equation is more accurate results for all real gases only above the critical temperature, and the result are acceptable below the critical temperature. And the equation completely fails in the transition phase of gas to the liquid below a critical temperature. So you can observe the graphs doesn't explain about the liquid form of gaseous or the gaseous, means it doesn't explain the transition phase from the liquid to gas. So that is the negative outcome. And here there is a conclusion part. By adding correction for interparticles attractions in particles volume to ideal gas, we can derive a new equation that more accurately describes the real gas behavior. That is the Vander Waal equation, which explains how the ideal gas is deviated from how it doesn't obey the also the at low pressure it behaves like an ideal gas, whereas at high pressure it behaves like an real gas behavior. How it behaves, that is the main on Vander Waal equation. Vander Waal made that there is an intermolecular force of attraction between the molecules, and that influence, that is the pressure influence is more influenced in that, and because of that there is a reduction of volume also. So there is a correction between the pressure and volume, we can say like. And lastly, I want to give one example, that is, consider the two piston, one piston of low pressure. If it is on the low pressure, then it behaves as an ideal gas behavior, means it shows the behavior of ideal gas. If it is at the high pressure, it shows the behavior of Vander Waals equation. That is the lastly conclusion. Thank you. And this is just a short summary of what is the experimental analysis done by the Vander Waal, the scientist called Vander Waal. Thank you.